Hey everyone, it's a real pleasure to be here. This is actually my first time at ClueCon. The other thing that I'll add is that I was not originally supposed to give this talk. Our company's developer advocate Fawaz, my colleague, was supposed to, but unfortunately he came down with COVID. So I am here. I'm the company's principal architect. We are a mid-sized startup, about 150 employees, based in Palo Alto, California, in the heart of Silicon Valley. Today I'm here to tell you about the best practices that we've developed around using our platform for real-time insights in mobility, telecom, and Internet of Things, including industrial IoT. The basic kind of outline of this talk is, number one, what is the Hazelcast platform? As I said, we are a relatively small company. Not a lot of people have heard of us. Raise your hand if you've heard of Hazelcast. Okay, you're my hero. Great. Next, a question I often get is, where can I deploy Hazelcast? Can I deploy it at the edge in an edge gateway? What kind of footprint will it run in? Can I deploy it in my own data center? Can I deploy it in the cloud? Is it cloud native? Does it run on Kubernetes or OpenShift or any of the standard container orchestration platforms? The answer to all of those questions is yes. I'll get into that a little bit more. We'll then talk about some real-world examples of Hazelcast use cases. We have a great one from industrial IoT, and then one that I think you guys here will really appreciate because it's from industrial telematics. We're actually doing connected vehicles in an industrial setting to reduce accidents. I'll also talk briefly about what other kinds of solutions you can build with Hazelcast, and finally, how you can learn more about Hazelcast. The one thing that I did want to say before I move forward is that the core of the Hazelcast platform, as anyone familiar with Hazelcast knows, is fully open source. It's licensed under Apache 2.0. We have a long open source heritage, and we were an open source project long before we ever became a commercial entity. And to this day, almost anything that I talk about, if I talk about a particular connector, like our Kafka connector, it's pretty straightforward. We're, as I said, an incredibly transparent company with an open source heritage. So if you just Google Hazelcast Kafka connector, you can see our documentation on it, and I believe the code for the connector. You can even see the GitHub project page for it. Here's the Kafka Hazelcast connector. With that said, I think I've said enough about what I'm going to talk about in our company culture, so let's kind of dive into the meat of this. We found that the real formula for success in a lot of sort of real-time areas in mobility, telecom, and IoT is the combination of high-performance stream processing with real-time machine learning. And by high-performance stream processing, we basically mean a true stream processing engine. So something like Spark or Flink or the Jet API within Hazelcast. There are two APIs in Hazelcast. I'll talk about them each in turn. But the basic idea is, you have this continuous stream of business events. You want to clean that data, filter it, do format conversion, ETL type operations on it. We have a lot of people in industrial IoT, right? That they have these ancient machine tools where they get data in some weird CSV format and they want to convert it into something like JSON or something that's semantically meaningful from a business standpoint, right? And then perform ML inference on that. And that's kind of what our platform is really about. The two APIs present in the Hazelcast platform are first the what's called the Fast Data Management API, which is also known as the IMDG or in-memory data grid API. So this is, we're a clustered solution, and we try to store as much of our data in memory as possible. It is durably persisted optionally, but if you don't have any need for persistence and you just want in-memory speed, we can easily deliver that. The fast data management layer is queryable through a SQL interface, even though it's an object store. You can think about it basically as being like a NoSQL database that stores as much of its data as possible in memory and will optionally tier to disk. And then, as I discussed, there's also our streaming compute API, which does all of the basic things that you would expect a streaming compute layer to do, like transform data from one format to another, which would be a map operation. You can also do a flat map operation. You can filter data. You can combine data in various ways, including rolling windows, sliding, tumbling windows, aggregates like rolling averages if you want to smooth telemetry or sensor data over time. This is very useful for things like quality of service metrics. And the other kind of cool thing that you can do is you can actually query the, if you want to think about the fast data management layer, we call it the IMDG or in-memory data grid API, the G in grid simply coming from the fact that it was designed as a distributed solution from the ground up. But just think about it as an in-memory database, basically. But you can query the in-memory database during a stream stage. The streaming compute engine is designed on a directed acyclic graph computational model, and you can actually see the visualization of the DAG here, and obviously each vertex in the DAG is a compute stage. That could be a data transformation, filtering, or it could be a combination of a kind where you do an enrichment. And that's what I was going to say is kind of cool about having the operational data store, the in-memory operational data store fused with the streaming engine. If you are doing something like predictive failure analysis for network devices, which is what one of our large customers in telecom does, and you have some kind of part of your wireless network infrastructure, and you try to detect anomalies about its behavior. Is its core temperature too warm or something like that? And what you might get is a device UUID, and you want to do a query to get a full set of information about the device, like what's its manufacturer, what's its model, what's its firmware revision, et cetera. You can actually query the operational data store layer from inside of a stream processing stage. So you could see that as mapping from device UUID, or in the sense of a mobile phone, an IMEI ID, into a full record about kind of semantically important information about that device. Lastly, I'll talk about this ML inference stage and how our ML inference runner operates. I'm just going to call it out now and then talk about it a little more down the road. But these are the two core components of the platform. Along with that comes an ecosystem of connectors, right? And these are connectors for, I mentioned the Kafka connector, but also for legacy message queues. The IoT connector is basically an MQTT connector. It's very easy to build your own connector, hence the custom connector, and we have a lot of sort of GitHub starter projects for this sort of thing. But the connector ecosystem is a big part of our overall, I think, product value proposition. One example use case I'll say that I mentioned kind of before is device anomaly detection, right? So you have a network device somewhere and you want to figure out, is it behaving aberrantly or is it likely to fail? So think about failure prediction and asset performance management, right? So you have this continuous stream of events that come in, and those go into the stream processing pipeline. The stream processing pipeline can execute through its machine learning inference runner any number of ML models, and those models can be written in Python. In Java, obviously, we're a JVM-based solution. They can also be written in native code in C++ that's accessed through the Java native interface. And then you'll often see results of stream processing results output to the in-memory storage layer. So that was the operational data store that I talked about, the in-memory data grid that's one of the two APIs in the product. Then you'll see it'll say clients, microservices. So imagine you're building a dashboard of all the things that are happening, a dashboard inside of your NOC, your network operations center, let's say, of things that are happening on your network, right? You can detect anomalies using the stream processing engine, but the question is, how do you build the web backend for alerting and things like that? And we would say that instead of using a traditional relational database where you have to deal with wrangling something into a schema, inserting it into a database, then you have an application server, your Tomcat, or if you're in the Python world, Flask, Django, whatever. Just forget about that. Just use the Hazelcast platform, and the operational data store and the streaming engine are integrated, and there's clients, as you can see along the top, for Java, .NET, C++, Node.js, Python. We've got a Go client now, as well as pure JDBC, which will allow you to kind of treat the fields in an object as virtual columns, so it'll create a virtual relational representation of your data. If you're interested in, as I said, in the same way that many RESTful endpoints are backed by relational data sources, it's pretty simple to take a Tomcat server and put a JDBC connector in there and then access data. Well, you don't actually need to be JDBCing against a relational database. You can do it directly against Hazelcast. A little bit about our kind of some of the ways that we've figured out how to do real-time machine learning well. One of them is that we have a very high-performance stream processing engine. And I'll show you some actual metrics around that came not from us, but from actually a third-party academic study that was conducted by some researchers at Cornell that looked at stream processing tools available in the industry. But we emphasize our interoperability with kind of ML runtimes very heavily, right? And we see machine learning as a core part of the stream processing or streaming analytics process. And one of the things that we've worked very hard to do is overcome this sort of impedance mismatch between the fact that most data science out there is done in Python, but then most of the actual data engineering that you do tends to be done in Java. So even though we are a Java solution and Hazelcast itself runs in a JVM, one of the things that we figured out how to do is to do a totally managed Python execution environment. It's not Jython, it's not Python on the JVM, it's actually CPython. And we will spawn as many CPython VMs as you have cores. So if you have a 2-core machine, you'll get 2 CPython VMs. If you have a 4-core machine, you'll get 4 CPython VMs. And this overcomes one of the problems with Python, which is, of course, the single interpreter lock, which basically makes Python a single-threaded language. And of course, this is controlled and coordinated through the Hazelcast DAG planner, which plans the directed acyclic graph, which you could think of as sort of like a query optimizer in a database. But to see some numbers, the Hazelcast Jet streaming engine with no parallelism and then to 4 cores, basically scales linearly, and this is a scikit-learn random forest model that we're running. So the next thing that I'll point out is that when you get into very significant Hazelcast clusters, this was 45 nodes, and it was running in AWS on, I think, C5, 9x large instances. We were able to do 1 billion transactions per second, and the P99 latency percentile was 30 milliseconds, right? So predictable latency and extremely high streaming data volumes. Of course, this is in a giant data center. You might also wonder, well, where else can I deploy Hazelcast? Can I put it at the edge? Yes, you can. We regularly deploy in these edge gateways, right, where we take data. You notice the add link one over here. I love the number of ports on this thing. Like, it even has like an RS-432, the kind of exotic, serial port from the mid-90s on there. So if you need to connect to some kind of exotic machine tool, you can do that. You can run the Hazelcast platform in the edge gateway. You can transform data that might be in a very primitive format coming off of machine tools into something that makes sense, right? Can you install it in the cloud or in your data center? Yes, you can. We can do a hybrid cloud deployment from on-prem into your cloud provider. We can do multi-cloud, one cloud provider to another. We have the Hazelcast Viridian managed service. Go to hazelcast.com and check it out. It's available on all 3 of the major public clouds. With that said, I promised that I'd get into some actual use cases. And we have about 8 minutes left, so I think this is a good time to do that. The first one I have is from is an IoT use case involving oil and gas field equipment monitoring. And so basically, edge computing cluster in truck, Sigma Stream. These guys do oil and gas exploration throughout Middle America. I think most of their operations are in the Dakotas. They just drive a truck out to wherever they're doing exploratory drilling, and basically on the drills they have all the sensor data that comes back, and Hazelcast, you can see here, is a huge part of ingesting that data, pre-processing the data, doing operational storage of the data that's in the in-memory data grid layer, and then doing actual decision making. And the decision making is about when do I take a drill bit out of service? Is it likely to fail? Should I keep drilling in this area, or is drilling in this area just going to be a waste of time? Hazelcast actually adjusts the rig settings in real time. So that pipeline is not only used for analytics, it's also used for decision making. So another use case that I'll bring up here is IBM is a key Hazelcast partner. We were part of their IBM Edge application manager launch. And we've done a number of major pilot projects with them. This is one that's ongoing right now in oil and gas. As well, actually I shouldn't say this is not an oil and gas project. The customer is a global Fortune 50 chemical company, although they are based outside of Houston, Texas, and the chemical work in question that they're doing is in hydrocarbon separation. So taking raw crude oil and turning some of it into gasoline and other parts of it into plastics and polymers. Some of this happens after raw refining. It then goes into this post-processing, hydrocarbon post-processing stage. But they've had a number of high-profile safety issues at this plant with vehicles carrying explosive compounds sitting next to each other, running into each other, or hitting trains, including a number of human fatalities. So we put together, along with our partners at IBM and Nokia, an industrial telematics use case. So basically monitoring driver behavior. You've got a fleet vehicle, it comes into the plant grounds, We give the driver of that vehicle an Android phone. There's a private LTE network that's deployed on the grounds of the plant. We try to detect bad driver behavior in real time, and then we also take all of the telemetry that we collect and then send that to the cloud, so that most of the stuff that we associate with data science and kind of statistical analysis gets done in the cloud. It doesn't get done at the edge. So Hazelcast tends to do very well in these edge-to-cloud kind of use cases. So a vehicle comes in, we aggregate the data into the Hazelcast IMDG operational store. Our stream processing engine then runs inference on the data using a number of ML models that are stochastic. We also run some deterministic business rules. IBM Event Streams then takes it up to the Azure cloud tier, which is based hundreds of miles away. The IBM Watson ML platform allows data scientists to work with this data. And then the cool thing is there's actually this arrow here, which I will show. It comes to this point here. So as we do obviously do inference at the edge, but we can actually update these models as data scientists back sort of at the home base look at the data. It's very easy for us to push new models out, and this is entirely enabled by our partnership with IBM around IBM Edge Application Manager. And if you just Google Hazelcast and IBM's Edge Application Manager, you can read the case study, and here on the IBM page we even have a white paper that we did with IBM on how we build edge-to-cloud applications together. So a few other Hazelcast use cases that I'll discuss that might be relevant to some of you guys in the room are in telecom. We've got wired and wireless network monitoring, network component failure prediction, asset performance management kind of stuff. Also real-time quality of service analysis. Basically anything you can take metrics or telemetry from, and you want to turn that into insights or decisions, you can use the Hazelcast platform for. In terms of mobility applications, pay-per-mile car insurance, we've got a customer doing that. Driver behavior analysis, I kind of discussed that in an industrial setting. You could also see pay-per-mile car insurance as a retail use case for the same thing. And then real-time telematics. In IoT, industrial process control, as in the Sigma Stream use case that I discussed, and then once again failure prediction and asset performance management. I said we have a pretty robust open source community out there and a large community of developers. So here's a QR code if you're interested in learning more about the Hazelcast community. We've also got a Slack channel that you can publicly subscribe to in your Slack client. We do quite a few Twitch videos. We sponsor some meetups. We've got some great blogs, and we've got our Hazelcast Heroes program. If you build a really cool solution on Hazelcast and you want to present with us at a conference, we would love that.